Good day everyone. So today I'm going to share with you a discussion video which it is all about the centroid of a region. So first we need to define what is centroid. So when you say centroid, it is the center of a mass of a geometric object to uniform density. So basically, this is all about geometrical center or the balancing point of a region or of a plane area. So in getting the centroid of a region, you need to consider two principles. First principle is the symmetry. So if the region has an axis of symmetry, then the centroid, which let's represent it as the coordinates bar and y bar, lies somewhere along that axis. In particular, if the region has a center, then the center is the centroid. So let's say we have our Cartesian plane here. I'll just write it here. And then we have our curve, which it will be represented by y is equal to f of x, right? Right. And we do have our axis of symmetry. So axis of symmetry allows us to have a two equal parts. So it means this part here is equal to this part here. So area 1 is equal to area 2. So to get the centroid according to the first principle, if you have an axis of symmetry, then the centroid lies on the axis, which it will be found in the middle because it's the centroid, it's the geometrical center. So therefore, this point here has a coordinates of x bar, y bar, which this is our centroid. Now, we do have our additivity principle, right? Or the second principle for centroid of a region. So if the region or if the plane area, bounded region having area A consists of finite number of pieces with areas x sub 1 a sub 1 to a sub n, and the centroids are x bar 1 and then y bar 1, so on and so forth, and then x bar sub n and then y bar sub n. Then to get the area, you need to consider, to get the centroid, you need to consider these equations. So for the x bar, you have x bar times a is equal to x bar 1 sub 1 times area 1 plus so and so on, x bar n sub n times area n. And then for y, that's y bar times a is equal to y bar sub 1 times a 1 plus and so on. You have y bar sub n times an. So when we consider additivity principle, we are considering the integral calculus. So if you have a curve here, let's say that this is our curve, right? This is represented as y equals to f of x, right? So in additivity, you need to consider a rectangular strip. So here we have our rectangular strips. I will just this one. It's a finite number of pieces. So the smaller the strip here, the better. The accurate approximation you could solve. So for example, these are our strip. It's an finite number of strip. So our centroid here is located somewhere here, right? So here we want to get the x bar. So if you want to get the x bar, you need to consider the area 1, right? You will use of the additivity. Then this is x1. So area 2, this is x sub 2. This is area 3. This is x sub 3. Area 4. This is x sub 4. Area 5. This is x sub 5. And so on and so forth. So that is why mapasok si integral calculus, because integral calculus will add them up, alright, from our lower limit, which is a, to the upper limit, which is b. Alright? So to get the center, you could use this formula. Right? You have x bar a is equal to integration of x times the dA, right, from your lower limit to the upper limit. Or to get the x bar, this is equal to the integration of x times dA from a to b all over a. So this is how you get for the constant value for the x bar, or the centroid, the distance of our centroid in terms of x value. Now, let's move on for the y. Alright, if we want to get the y bar, we need to consider the same curve. Alright, so let's say again, we have our curve, which it is equal to y equals to f of x. Then this is our lower limit a, upper limit b. And according to the additivity rule, so you need to have a finite set of rectangular shape or area. So if you add them up, you get the total area. So where your integral calculus belongs to or can be applied. So let's say that the centroid of this region is somewhere here, right? So now this is the rectangular shape and this is the area. Let's say we have our dA here. And then to get the distance from here to the axis of rotation, we need to know the distance from the curve to this part, which is, this is y. So the distance from the curve to the x-axis is y. Therefore, this one, because it's in the middle, therefore this is y all over 2. So to get y bar, this is equal to the integration of y all over 2 times the dA from a to b all over a. So y bar is equal to 1/2 integration of y dA from a to b all over a. So this is the formula of getting the y bar. So to further understand this concepts, maybe we will have some example. So let's try to find the centroid of the area in the first quadrant and the curve y is equal to 4 minus x squared. So our parameters are the first quadrant and the curve. So in the first quadrant, x is equal to 0 and y is equals to 0. Yung i-consider natin na boundaries and the curve. So first thing you need to do is to know the details of your curve. You need to find the vertex first. So you have y is equal to 4 minus x squared. So this is equal to y plus, minus 4 is equal to negative x squared. Therefore, our vertex is 0. This is plus a 0 here. So we have 0, 4. Right? That's our vertex. Now, we need to get the point of intersections or intersection points, which at x equals to 0, one boundary is our first quadrant in terms of x. So that's x-axis. So x is 0, y is 4 from here. Right? At y is equal to 0, that 0 is equal to 4 minus x squared. So we have x squared is equal to 4. Get the roots of both sides. So this is equal to x, positive, negative 2. So therefore, our intersection points are 0, 4, and positive, negative 2, comma 0. Take note, we need to consider the first quadrant lang. So we need to get the positive value. Right? So let's try to draw our curve. So our curve is facing downward because we have a negative lattice rectum here, so it is downward, and the vertex is at, let's say this point here is 0, 4. and this point here is at 2, 0. So our curve is facing downward. So this is our curve, which is y is equal to 4 minus x squared. Right, our goal is to find the centroid, which is somewhere located here. Let's say it's like here. So the first thing that you need to do is to get the area, all right, of this bounded region. So this is our centroid again, x bar, y bar, right? So to get the area of the bounded region, you need to make use of the vertical strip. So you have your vertical strip here, right? Let's try to get the area first, which this is dx, right? The distance from the upper part of your strip to the bottom part is equal to y. Alright, so to get the area, this is equal to the integration of y times dx, and then we will run that area from your lower limit a to the upper limit b, where our a here is at 0 and then upper is 2. Take note that we only need to consider the first quadrant. So you have a is equal to the integration of y, which our y is the curve, right? So that's 4 minus x squared times quantity dx, right? Take note that this part here is y equals to 0. That's the x-axis, and then this is the y-axis. So that's 4 minus x squared from a, which is 0, and then our b, or upper limit, is 2. So getting the area, this is equal to 4x minus x cubed all over 3 from 0 to 2. So substitute the upper value and then the lower value from this equation. So you have 4 times 2 minus 2 raised to 3 all over 3 quantity minus quantity 0, which area is equal to 16 all over 3 square units. So therefore, our area is equal to 16 over 3 square unit. Now, we are getting the value of x bar, right? So getting x bar, that is equal to integration of x, right? Your x here is the distance from here to this part of your strip, right? So this is x. That's x times dA, right? That's the area, which is this one, right? This is your dA. Integration of y dx from a to b, that's equal to a. You just simply write a there, or this equation here. This is equivalent to your dA. Integration of quantity 4 minus x squared, quantity dx from 0 to 2. Then, from 0 to 2, it's still the same ang ato ang parameters because we need to get the centroid of the same area. So, that's a to b, which is 0 to 2 all over a. So, we already have the value of a, which is 16 all over 3. Right? So, maybe I will move it on our next page. So, getting the x bar, that was equivalent to integration of x dA from a to b all over your area. So now we have x bar is equal to the integration of x times dA, which is your curve times dx. That's 4 minus x squared times dx from 0 to 2 all over your a was 16 all over 3. So we could solve for the x bar now. X bar is equal to 3 all over 16 integration of 4x minus x cubed times dx from 0 to 2. So you have 16 whole over 3. This is 4 times x squared all over 2 minus x to the fourth all over 4 from 0 to 2. Now we have 3 all over 16 times substitute the value of 2 to our upper, which is our upper limit sa atong equation. So you have 4 times 2 raised to 2 all over 2 minus minus 2 raised to the fourth all over 4, right? Minus, because it has x on each term, so 0 na yan. 3 all over 16 times 0, and then this is equivalent to 3 fourths. Alright, so therefore our x bar is equal to 3 fourths. Now, we need to get the y bar. So, in y bar, right, it has a formula of integration of y all over 2 times dA, right, from a to b all over a, right? So, as you can see, kanina with our curve, so I'll just draw it here. So, this is y, right? Therefore, this is y all over 2. Okay? So, you just divide y by 2, right? Actually, this is our x bar, y bar here. So, y bar now is equal to the integration of y, which our y is the curve. So, that's 4 minus x squared all over 2 times the dA. That's the formula for the area. That was 4 minus x squared times dx from 0 to 2 all over our a was 16 all over 3. So, y bar is equal to 3 all over 16 times 2. We have 2 here, that's 32. So, again, 3 all over 16 times 1 half, times 1 half, that's 3 all over 32. Integration of 4x squared times 4x squared, right? 4x squared quantity times quantity 4x squared, that's 16 minus 4x squared minus 4x squared, negative 4x squared minus 4x squared, that's 8x squared, right? Then negative x to the second power times x to the second power, that's plus x to the fourth dx, right? We just expand it from 0 to 2. So you have y bar is equal to 3 all over 32, right? We can get the integration of this. Let's try to evaluate it. 16x minus 8x cubed all over 3 plus x to the fifth all over 5 from 0 to 2. Substitute the upper limit and the lower limit. We have 3 all over 32 times the quantity of 16 times 2 minus 8 times 2 raised to 3 all over 3 plus 2 raised to the fifth all over 5. Quantity minus 3 all over 32 times 0. So y bar is equal to, just input this in your calculator, it is equal to 8 all over 5. So therefore, our centroid is at 3 all over 4 and 8 all over 5 for the y value. So this is the coordinates of our centroid.